Okay, so what you're going to do is you're going to practice in here. We're going to be calculating compound probability. This is a huge part of the test, the overwhelming majority of the test. And I'm going to just say that you need to really pay attention and go through the process because it's easy to miss on these. So here we go. Let's take a look. We're calculating compound probabilities with and without replacement, right? And here we go. We're going to start by looking at, here we have two cards from a standard deck of playing cards, one at a time with replacement. So now we're going to be looking at, we'll do a couple of things in here. Let me get my edit tool here out and just really quickly add some text in here. So the first thing is there are 52, right? Oops, there are 52 decks cards in a deck, right? Cards in a deck, so you should know that. There are 4 suits. By the way, you don't have to know these facts if you don't know your cards very well. There are no questions on the test that involve suits and cards and stuff. So there are 4 suits, right? They're like hearts and diamonds and spades, right? And clubs, right? So, and there are 13 I'll just say values, right? Because they go from ace through king. Okay, so total of 13 in each suit, and then each suit, 13 times 4 is 52. So that's just a basic fact that I'm telling you now because we're going to want to use that. Oh, man. See if I can. Oh, that's horrible. All right, hold on just a second. Sorry. Okay. So, so what I'm going to do, I'm going to just move that. I'm so sorry. Here we go. Let's, I don't want to, gosh. I'm going to just try to move this guy. There we go. Get him out of the way. That's a basic fact, okay? All right, we're going back to now take a look at this thing. So the key here is to recognize that because you're replacing the cards, right? It says with replacement here. Because you're replacing the cards, this is going to be a independent event. And we have an AND situation. So let me see if I can get over here and pull up this note here. So if I've got independent and AND, all I'm doing is multiplying, right? So this right here, you were supposed to fill this in. I would definitely be putting this in my notes in a minute when we do notes. You're going to have this in there, okay? So it's basically, the probability of the first event times the probability of the second event. That's for independent events, right? Oops. Let's see if I can get that there, right? So if it's an independent event and you're doing the AND, it's A times B. The probability of A times the probability of B. So what is the probability of getting an ace first? So that would be, what, 4 over 13, right? I'm sorry, 4 out of 52, because there's 4 in the deck that are aces. And then he puts them back, and then a 10, there are 4 10s out of the 52 in the deck. So you could put that together, you'd multiply it, and you'd get your answer. All right, here it says an ace first or a 10 second. So now this is different, right? You have to add the probability of the ace to the probability of the 10, and then subtract the probability of both. And to get the probability of both, we're multiplying. So, probability of both is right here. So you're going to be saying it is 4 over 52 plus 4 over 52 minus, and then 4 over 52 times 4 over 52. So if you do that, you will get your answer for this problem, right? An ace first or a 10 second. And the reason is, again, we have replacement, and this is an OR, so replacement makes it independent, or makes it this formula here, okay? All right, what about 2 diamonds? So with 2 diamonds, you have 13 out of 52 And to get 2 diamonds, you would have to do that twice. So the first time you would have 13 out of 52, and the second time you would still have 13 out of 52. Why? Because you replaced that first card. So there are 13 of them that are diamonds, and then 13 of them again that are diamonds. Okay, here we go. Any pair. Okay, so a pair is going to be, the first event would be drawing any card, right? So that any card comes out, that's fine. That's 52 out of 52, which is 1, right? And then the second event has to also happen, right? But here's the trick, right? It has to match the first card, and there are only 4 cards now in the deck that will match the first card, right? So if you got, let's say, a 7, and that could be any card, but we'll just say a 7, and you put the 7 back in, the second card, when you pull it, there are 7 more in there, okay? I'm sorry, there are 4 7s in that deck, so it's 4 out of the 52. Okay, I hope you can follow that. All right, now if you did not replace them, we're going to be using this formula. This is for not replacement, right? And in this case, you're going to be taking, well, let's see. First, it's going to be dependent. When you take it out and it's no longer there, then you're going to be dependent. So here we go. So if I took an ace first and then a 10 second, so what's the probability of getting an ace first? So the probability of getting an ace first would be 4 out of 52. And then what's the probability of getting a 10 second? Well, there's still 4 10s in there because I still have 4 10s. But now I only have 51 cards left for this second one, right? Okay. So now we have an ace first, and that's if we're trying to find the probability of both, because there's now only 51 in there. So what's the probability of getting an ace first or a 10 second? So it says here we're going to take the probability of the ace plus the probability of the 10 minus the probability of the ace times the probability of the 10, given that the ace was already drawn. So here we go. Probability of an ace, 4 over 52, times the probability of the 10, 4 over 52, right? Minus the probability of the ace, 4 over 52, times the probability of the 10, given that you've already drawn the ace. Okay, so there's your formula there. Okay, now notice, really, I'm just trying, the biggest thing you're going to need to be doing here, if you've got access to these formulas, is to just recognize, are they independent or dependent? And are we talking about an and situation or an or situation? And then this really benefits people very well who do a good job of reading through and decoding the problems, because that's really what it is. All right, 2 diamonds. So if I'm going to do 2 diamonds, then the first diamond, I would have a 13 out of 52 chance, right? And then the second diamond, because I'm not putting it back, there's only 12 left, right, out of 51 cards remaining. Okay, so that's just what you have to think about. You've taken 1 card away, and the one you took away was a diamond, right? So what about any pair? Well, so the first time when you draw a card, you would get, what, 52 out of 52. So that's 1, right? But now the second time, considering that you're holding 1, there are only 3 cards left that can match that one you're holding out of the 51 cards still in the deck. So there's your probability formula right there. Okay? And how did I do these? Well, these are dependent events because we're not putting them back. And so we're looking at the dependent events is probability of A times probability of B given A, and we're just thinking it through. After you've taken one out, the probability for B changes given that A has already happened. Okay? All right. So here we go. What if there's more than 2 compound events? So we're going to start with replacement. So if I'm going to get 3 of a kind, and I'm putting them back. Well, that means, you know, the first time I'm going to draw 52. I mean, I can get any of 52 out of 52, and that's fine. All right. Then the second time, though, I need to get 4 out of the 52 because I put them back. There's still 42, and there's only 4 matching ones to what I got the first time. And then the third time, there's still 4 out of 52. And here's what I figured out. This is how I know to do this. First of all, it says with replacement. So with replacement means independent, right? And then the probability of events occurring repeatedly is just found by multiplying the probability of those events repeatedly. So, you know, since the probability isn't changing, it's just going to be over and over and over again. Now, the reason why we're going 52 out of 52, just realize, is because we get to match any card that gets drawn first. So the first card really doesn't matter, right? If you take a 3, then you're looking for another 3, and then you're looking to find another 3. And it can be the first 3 that you find again. So if you got the 3 of hearts here, right? Well, and then you put it back. If you pulled out the 3 of hearts, that counts, right? That's the second time you get the 3 of hearts. Put it back, you get the 3 of hearts again. That's 3 times. So notice that, you know, the probability here isn't going to change no matter how many times. You're just going to keep multiplying for 4 of a kind or whatever. But here, the first time you can match any card, so it's 52 out of 52. Okay? But getting 3 kings is a little different because now it has to be a king. So the first time is going to be 4 out of 52, right? And then the second time is going to be 4 out of 52 because we've got to match it. And then the third time is going to be 4 out of 52 as well. So now getting 3 kings, starting to get unlikely that you would exactly get 3 kings. All right. Now, if we do not put the cards back and we're trying to draw 3 of a kind, well then you have 52 out of 52, whatever that first one is, times, now there's only 3 cards remaining out of 51 in the deck, right? And we're going to multiply that by, now there's only 2 cards remaining because we're assuming, the assumption is that, like, let's say you got a 7 here. Well, now it's out of the deck. There's only 3 7s left out of the 51 cards. And by the time you're going for that third card, there's only 2 7s left out of now just 50 cards. So you just got to think your way through that problem and realize we're talking about 3, you know, these are, looking at our chart here, right? These are 3 dependent events, right? Because we didn't put the card back, so now it's dependent, and the probabilities are changing, and it's up to you to think through how they're going to change. But because we're talking about to get 3 of a kind means all 3 things have to happen. You have an and situation here, so we're looking at this thing over here. Okay? To get 3 kings, okay, so again, this is an and situation. I have to get all 3 of them, right? And because I'm not putting the card back, I am still doing a dependent event here. So the first time getting a king is a 4 out of 52, right? The second time getting a king is 3 out of the 51. And the third time getting a king is 2 out of the 50. Okay? So it says, what kinds of events generally correspond to situations with replacement? So those would be, with replacement generally means that, you know, they're independent, right? And without replacement generally means dependent. Because when you replace, you, you know, repeat the experiment, right? You repeat it exactly when things have been replaced. But when they've not been replaced, you're not repeating the experiment, you're modifying the experiment, okay? All right, compound events without repetition. So now it says, calculate the probability that Bill, George, and Rio are randomly selected to serve on the committee. And the Homeowners Association has 25 members, so they're going to pick 3 people out of 25, and obviously we're not repeating anyone. So now the question is, you know, what is the probability that these 3 people are the ones picked? So we're looking for these 3 specific people. So what is this now? Well, this is, if it's not repetition, if we're not repeating people, then what do we have here? Right? We have a dependent event here, right? It's dependent. So, you know, each member has a different first name, by the way. So you can't just say, oh, there might be 6 Bills in there or something, right? There's only one Bill, there's only one George, and only one Rio. So the probability of getting any of those guys here, well, what would you say here? I want you to just pause and think for a minute. See if you can figure this one out on your own. Okay, so now the way that it works, you're basically, you can think about this like the same way as the deck of cards. What's the probability of getting any of these 3? Well, and notice that once we pick one of these 3, then the probabilities are going to change of who's left, right? So just so that you can see, this is a dependent event. Once we pick one of them, it's going to change, right? And we're trying to find out the probability that all 3 happen, so we're going to be just multiplying, okay? So what's the probability that Bill, George, or Rio get picked first? So that would be 3 out of the 25, right? Then we're going to multiply by 2 out of the 25, right? And then we're going to multiply by the last one out of 20. Oh, wait. Sorry, it's not 25. There's only 24 people left, right? Ooh, maybe you caught that already. And then 1 over 23. So out of the 25 people, there's 3 that can get us started here. But then after, assuming that Bill's already been picked, right? Then there's only George and Rio left to be picked out of the 24 remaining. And then once George gets picked, then there's only Rio left out of the 23. So the probability that all 3 of those get randomly picked is done like this, okay? So now we're going to say, instead of saying that, anybody can get picked first out of those 3, instead, now we're going to say the probability Bill is randomly selected as president. So if Bill was randomly selected, but now as the president, right? That means the probability is 1 out of 25 that Bill will get selected. That's the first event, right? And notice that they're asking it in such a way, they're saying and, right? So they're asking us, what is the probability all 3 of these things happen, right? And once Bill is selected for the president, then we're going to calculate what is the probability that George gets selected as the vice president. Well, sorry. Hold on just a second. I lost my train of thought. Okay, so Bill was selected as the president. That means we have to select, a vice president, and we're not going to include Bill, right, because he was already selected, so we go 1 out of 24, and then we would not include Rio, and 1 out of 23. Let me tell you why I got a little distracted here, or confused for just a second. I lost my train of thought. So what I started to think about, I was going to say Bill got selected first. But it really doesn't matter if they pick the president first, or if they pick the vice president first, or the treasurer first. It really doesn't matter. Assuming that they can't serve in all 3 positions, if they started by selecting the treasurer and they said, we need somebody really good as a treasurer, and Rio, he's an accountant, he's the best guy to get, so let's pick our treasurer first, it would still be 1 out of 25, right? And actually, I'm so sorry. They wouldn't actually do it that way because Rio is not, that would not be random, right? And it says that they're randomly selected. So if I said, oh, Rio is an accountant, he's the best, that would not be a random selection, right? So I'm so sorry, I shouldn't even say that. See, I get myself confused going through these late at night, and I'm sorry about that. But the bottom line is, if we randomly picked the treasurer first, it would still be 1 out of 25. And then if we wanted to pick, either of the others, you can see that the number of people remaining would go down. But we're only looking for one specific person for each one, so that's our calculation model there. All right, now what's the difference between these 3? Well, the difference is that these 3 are people being picked for, the committee, and it doesn't really matter what order they got picked in. In this case, order does matter, right? Because we're looking specifically for one person here, one person there, one person there. So that's the big difference there. All right, what about 5 particular members being chosen to serve on a 5-member committee? So that one, you would, say, okay, well, we have 5 out of 25, right? What about after that? There'd be 4 out of the remaining 24, and 3 out of the remaining 23, etc. 2 out of the remaining 22, and 1 out of the remaining 21. So that would give me the probability of the 5 particular members, if you name 5 people, being chosen to serve on a 5-member committee. So now, calculate the probability of a particular member of the homeowners association being chosen to serve as one of the 5 officers. So, if I had the first, okay, so I'm sorry, let's just say Steve was going to get picked to be an officer. So just making sure I understand. It says the probability of a particular member. So we'll go with this guy named Steve. He's one person out of 25. So what's his probability of getting chosen to serve as one of the 5 positions? Well, his probability, okay, so sorry. Look. Steve, this is a different one. Because now if Steve gets picked first or second or third or fourth or fifth, that's a different scenario. He's still on the committee, right? I didn't misread this, did I? No. No, I don't think so. Okay, but here we're saying one person to get chosen in any of the 5 events. So this is no longer an AND event. This is an OR event. So now we have, and it is dependent. It's a dependent event. And so we're going to have to use this formula here. Okay? Excuse me. Okay, so this is an OR situation, right? So in the OR situation, what we do is we're adding together the probability of each of the events, but we take away the possibility that multiple events can happen. All right, so let's go through that and let's think about this, okay? So Steve is the particular member, and what is his probability of being the first person picked? Well, that's 1 over 25, right? And we're going to add that to the possibility of his getting picked for as the second member, which was, there was 1 out of 24 there, right? And then there'd be 1 out of 23 is his probability being picked as the third member, and then 1 out of 22 is the fourth member, right? And then 1 out of 21 as the fifth member. But remember that we have to subtract the probability that he got selected more than once. So in this case, what's the probability that he got selected more than once? Well, it's not. It's not possible that he gets selected more than once. Okay, it's impossible for him to get selected more than once. So we do not have to subtract. There is no probability of him being picked once and twice, right? The first time and the second time. Okay, so this is the formula. So we would be subtracting 0 from those probabilities, right? So it's just basically this. Now, how would you work this through? So, important to think about, like, defining the events. What's the first event that happened? So we call that A. Event A is being picked first, right? And event B is being picked second, right? And event C is being picked third, right? And event D is being picked fourth, right? And then event E would be picked fifth. So the reason I'm writing these out, right, is because I think it's important for us to make sure we keep track of what's happening with these events, right? And then we have to consider, what is the probability? Can Steve be picked more than once? Well, no, not if they're planning to make a 5-member committee. So therefore, this possibility of the AND, right? So, so the probability of A, and any other event happening, right? So we'll just say the probability of any, I guess probably better, any 2 events would be equal to 0, because the probability, if he gets picked first, then he cannot be picked second, right? So in this case, you're using the probability of A, given that he was already, it says probability of A and B, given that A already happened. So, B, given that A already happened, if he was picked first, then the probability of B happening is 0. It goes to 0, right? Because A's already happened. So now if you want to multiply together to find out the probability of A and B, a second B given A, this would be 1 out of 25 times 0 over 24, because B cannot happen, and when you multiply it together, you get 0. So that's where that comes from. Okay, so it's good to really write these out. I'm just really strongly been teaching that and really want you to think about that. Okay, so now we're looking at, we're going to be getting into and or problems here. And this says, the menu at a local restaurant offers the items shown. A dinner consists of one selection from each category. So how many different dinners exist? So remember, a dinner, a dinner equals one appetizer plus one salad plus one entree plus one dessert, right? So now they want me to find out how many dinners exist. So I'm going to be calculating, what I'm going to be calculating here is how many total ways can these 1, 2, 3, 4 things happen, right? So how would I do that, right? So it would be, I have 4 actions. I have the action of selecting this, selecting that, selecting this, and selecting that. And when we talked about sample spaces, we said, you're going to take each action that's going to happen here, and you're going to count the total number, and that's the counting principle, right? So for my appetizers, I have 1, 2, 3, 4, 5. So I have 5 different appetizers, right? And the counting principle tells me to multiply, right? So how many salads do I have? 1, 2, 3, 4, right? And then how many entrees? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So times 10, right? And then how many desserts? 1, 2, 3, 4, 5, 6, 7. If I counted that right. 7. So that would be my answer for how many different dinners exist, right? Now what is the probability that they select chicken? Well, they're going to be selecting chicken from out of the entrees, right? So do I have to pay attention to any of the others? No. I just count those entrees and I have what? 1 chicken out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the probability of selecting chicken is 1 out of 10, right? 10 entrees. What is the probability they select meatloaf and chocolate cake? So now we're doing meatloaf and chocolate cake. So this is an and. Now I'm getting into compound probability, so let me go back to my chart. It's an and, so I'm going to be looking at this side here. Now the question is, are they dependent or independent? So the fact that he has already picked, let's say, meatloaf, does that change the probability or his choices in the desserts? And the answer is no, it doesn't change. He can still pick whatever he wants. So these are independent and events, and all I have to do is multiply together. So that's what I'm going to do here. Meatloaf and chocolate cake, so 1 entree and 1 dessert would be, the probability would be equals 1/10 times 1/7, right? That will give me the probability they picked meatloaf and chocolate cake. What is the probability one patron selects steak or another patron selects pie? So, okay, let's see. First of all, it's an or statement, so I'm going to be using my or statement here. And then if somebody picks steak, does that have anything to do with somebody else picking pie? No, they're not related at all. If it's different, a patron is a person who shops, right, or goes and visits the store and spends money at the restaurant, right? So it's a diner is another way to say, or somebody who's going there to eat. So if one person went there to eat, picked steak, and a different person selected pie, these are completely independent events, and we're trying to find out or. Okay, so now here we have the first person picking steak would be 1 out of 10, right? And we would add to it the person picking pie, 1/7. And now we have to ask the question, should we, what is this part of it here? So we need to subtract what's the possibility that we've already counted them, right? So the intersection of those two things. Okay, so, think about what are we going to need to subtract here. I'm going to pause this and let you. Okay, so hopefully you've been able to think this through, right? If I said one person selecting steak, now maybe what I should do, let me see if I can draw this out real quick, all right? So if I had a little table, right? Oh boy. Okay. Let's see if I can erase that. Start again. Okay, let me get a little box here. So here we go. So if I'm going to have a little table, right? So I'm going to think about the first person, and I'm going to try to make this into a line. So the first person, see, hopefully I can do this well. Okay. So we have a first person and a second person. So notice that, and this is really good, helpful if you get yourself in a situation like this where you're not 100% sure. But what we're going to do is I'm going to put in a little text here, right? So this is the first person, so this is person 1. And this is the second person, person. Oh, what happened? All right, I'm really sorry. I don't know what's going on with that, so I'm going to just close that for a minute and see if I can just talk you through it. So if one person has steak and another person picks pie, so and it's an or situation. So the first situation, now you see that table in your mind right here, I would have they picked steak and a dessert, right? So they could pick steak, they could pick pie, and if they pick steak or pie, we would circle that, right? Those are, the possibilities there. And then if the second person picked steak or pie, we would have the steak circled and the pies circled. I'm going to get myself confused even talking this through. But the bottom line is, I'm really sorry. I don't know why my technology is failing me here, but the bottom line is that the probability that a person selects steak or a person selects pie can include an overlap where we have somebody pick steak and pie. So we have to subtract here, right? We're going to have to subtract. And the way we subtract is the probability that both events occurred, right? Because we don't want to overcount them. So there's our formula, and it exactly matches this formula here. The probability of A picking steak, probability of B picking pie, minus the probability that somebody picked steak and pie. Okay? So those are independent events there that we're using the or on. So now it says, what is the probability that a patron selects meatloaf, any entree except meatloaf? And I'm going to say the probability that a patron selects meatloaf is equal to 1. So the probability of meatloaf, I think that was equal to 1 out of the 10, entrees. So the probability of the complement to meatloaf, which means anything but meatloaf, right? And I don't have the tools to write this, really the way it should be written. But, and it doesn't look like, oh, maybe I can stretch that out there. Okay. So the probability of the complement to meatloaf is anything but meatloaf, right? And so that would be 9 out of 10. And just remember that a probability of an event and its complement always add up to 1. So this is everything except for that. Okay, what is the probability of patron selects flounder, Caesar salad, and fruit? So this is a multiple events here, and we're doing and. If they pick the Caesar, they pick the Caesar salad, pick the fruit, those are all independent events. So this is an independent and, so I'm just going to multiply. So the flounder was 1 over 10, and then we multiply by the salad. How many salads were there? 4, I think. Yeah, 4 salads, so 1 multiplied by, so 1 out of 4. And then, oh man, the fruit. What was the fruit? Fruit was one of the desserts. Okay, so there were 7 desserts, right? So we're going to go back down here. So times, 1 over 7. Okay, that's the probability they're going to select one of those 3 things. So what is the probability a patron selects pizza, cookies, and any salad except garden salad? So this is the entree, that's 10. This is cookies, that is 7. There were 7 desserts, and salad except, that's there. So this is a not salad situation. But they're asking again, and. So this is again an independent and event, right? And pick anything I want. For my entree, I have 1 out of 10 choices for that. And I have 1 out of 7 choices for my cookies. And I have 1 out of, oh, wait a minute. Now they're asking me any salad except garden salad. So there are 3 choices out of the 4 for garden salad. So I got to be careful about that, right? Okay. There's a probability that a person selects soup, chicken, any salad, and any dessert. So soup, there were, oh my gosh, I think it was what, 1 in 5 soups? And I didn't remember. Appetizers, there were 1 in 1, 2, 3, 4, 5, 6. Oh no, wait, 1, 2, 3, 4, 5. So, okay, so what is the probability? Let's see if I can remember this all. What is the probability of soup? And this is again and these are all independent events, so I'm just multiplying. So the probability of and 1 over 5 for my appetizer times 1 over 10 for my entree times 1 over 4 for my soup, chicken. 4 out of 4, 4 over 4 for my salad, right? And any dessert is 7 over 7, right? So, you know, you might be able to figure this out here, but we're looking at 4 over 4 being 1, right? That's 1. So clearly, if we're multiplying by 1, these numbers really aren't that important. So really, they're just asking us if they select soup or chicken, right? Soup, chicken, soup and chicken, really. Okay. So that is the last we'll do here. You can practice these if you want and go back through, but I'm going to end this recording and get you guys ready for your notes so you can take your test on Thursday.